Good afternoon. So today we're going to talk about the cross product, which is yet another special operation involving vectors. And as it happens, as I prefer to do in many applications like this, I would like to take it slow, postpone a little bit how the operation is defined and how it's computed, because I want to emphasize as much as possible the motivation for this type of construct. So this allows me to actually go over some other examples with the concepts we already talked about. But I think it's also important always to remember that these operations are not really arbitrary, because if you just start with the way this operation is defined and how it's computed, it's not really intuitive why it's defined the way it is. So let's start with a little bit of motivation. It's not, by the way, the only use of the cross product, but it's the easiest one to go over as a starting example. So suppose we have two vectors, and for simplicity, let's actually use actual vectors with actual numbers, not generic ones. So let's say we have a vector a bar given by the components 1, 1 minus 1. So again, as always, a vector in the component form, and another 1 b bar given by the components 3, 1, 1. And the goal is to construct a vector perpendicular to the plane determined by A and B. Okay, so if you imagine A and B starting from the origin, they form a plane. We want a vector perpendicular to them. Now notice I'm going to be a little bit vague now, because I'm not going to say anything for now about the magnitude nor about the orientation of this vector perpendicular to this plane. So obviously, if I don't specify anything about this, then there has to be infinitely many traces, right? There's plenty of vectors you can construct perpendicular to the plane determined by two vectors. This is kind of a messy here, so let me actually again do it here, so I can clearly see a plane here. So that's the vector A, that's the vector B. We want to figure out a vector perpendicular to two of them, to the plane determined by the two, A and B. So to anticipate a little bit, this special vector will be actually the cross product between A and B. The answer to this question will be the cross product. But let's see how we can actually figure this out, how we can compute such a vector just based on the stuff we learned already. So remember, we talked about the dot product in the previous lesson, right? So this unknown vector that I tried to compute, let's suppose it has the components u1, u2, u3. So because I wanted to be this guy to be perpendicular to the A and B, remember that whenever two vectors are perpendicular, the dot product between them should be equal to 0, right? That's a consequence of that cosine formula between the two vectors, right? So if perpendicular, it means dot product between them should be 0. So let's see what this dot product actually entails for the three examples I picked. So the vector A is 1, 1 minus 1. Let's compute the dot product. So that's going to be u1 plus u2 minus u3 equals 0. And then the dot product with the second one, 3, 1, 1. That gives me 3u1 plus u2 plus u3 equals 0. So I'm supposed to find u1, u2, u3 from two equations. Now, from some basic linear algebra, we kind of tell already maybe with some manipulation, like if those of you took some basic linear algebra, there is that concept of row echelon form or Gauss Jordan elimination. We don't have to get too deep into that, but just by looking a little bit and manipulating the terms, you kind of see that this system will have infinitely many solutions. And that's all good, because remember, I anticipated that unless I specify the magnitude and the orientation, there has to be infinitely many vectors perpendicular to the plane determined by A and B. So how do you solve a system like that? Well, typically you solve it in terms of an arbitrary parameter, one or two of them. But I mean, in this case, you will see you could solve actually for two of the unknowns in terms of a third one. And actually, it doesn't matter which one you pick to be arbitrary. So I'm going to just do some ad hoc elimination. For example, I can add the two equations because I can quickly eliminate u3. So that gives me 4u1 plus 2u2 equals 0. Let's divide by 2 both sides. And it looks like it's probably easier to just choose u1 to be an arbitrary parameter, because I don't want to make any fractions by division to 2. So for example, u2, I can get it in terms of u1. So let's keep it like that. So u2 is minus 2u1. And let's make a quick substitution into the first equation, for example. From the first equation, I get u1 plus u2 equals u3. And so plug in u2, like plug in minus 2u1 for u2, and that gives me that u3 equals minus u1. Okay, so pause for a moment if you need to, but notice that so far the vector that I was trying to construct, perpendicular to A and B, in the order of the components, is given by u1, u2 which is minus 2u1, and u3 which is minus u1. And using some scalar multiplication in reverse, that's going to be like a scalar multiple of 1 minus 2 minus 1. So this is, you can take this u1 to be arbitrary. So basically, pick your choice, any multiple of, so any scalar multiple of 1 minus 2 minus 1 will serve the purpose of being a vector perpendicular to A and B. So here's come the whole idea with the conventions that we talked about before, like the right-hand rule or some other elements that will come up later. You have the freedom to choose any magnitude you want, any orientation you want. How do you choose the one that is most useful? This comes from lots of tools that you develop with these operations. And people who actually invented this realize that if they make a consistent choice across the board, things will be less confusing along the way. So this is where it comes into play, again, the convention about the right-hand rule. So the first remark here, the orientation of this vector will come from the right-hand rule. So let's actually be more specific here, right? So I mean, of these multiples of 1 minus 2 minus 1, one of them is going to be designated to be the cross product, right? So in other words, given two vectors A and B, the vector perpendicular to A and B is going to be the cross product, which is another vector, by the way. We're going to define it more formally on the second page, so the notation for it will be A cross B. So I'm going to write the full definition and notation on the second page. But that is the idea. So let's actually use a different color still here. So if you imagine that, let's say the vector A is like that from your perspective, and the vector B is like this, we're going to choose the orientation for the cross product so that the cross product, which is another vector obtained by solving the system I was talking about here, is going to be oriented according to the right-hand rule with A over B. In other words, when you do the right-hand rule, your fingers on the right hand will be aligned with the vector A, and your hand is going to be aligned with the vector B when you compute in this order A cross B. Excuse me, made a mess here. So when you compute A cross B in that order from left to right, that's how you align the fingers of the right hand. And obviously the A cross B, the cross product will be along the thumb, right? So the thumb of the right hand will point into the direction of A cross B. So that establishes how you pick the orientation. We'll get to the magnitude later on the second page when I define the formulae. The magnitude is not going to be that obvious right away why it's chosen to be that way. But with a couple of applications, I hope it's pretty clear why it's convenient to be. So let's recap a little bit before we move on to the second page. For now, one motivation for this new operation, this new vector, is to construct a vector perpendicular to the plane determined by A and B. It's pretty obvious when you try to find such a vector, right, using some system that comes from the dot products. It's pretty obvious you have infinitely many traces. To be more specific, you have scalar multiples of a specific vector. How do you choose one of them so you can have only one default cross product, so that you can actually have an operation, right, of the two vectors? Orientation will be chosen such that the vector, the cross product, points into the direction of the thumb using the right-hand rule, and the magnitude will be again chosen in a specific way to have a certain property related to the angle between A and B, which I'll mention it on the second page. Before I move on with the second page, once again notice that I know already, I mean, you should realize already that the cross product is not going to be commutative. In particular, because if I do instead B cross A, again, according to the right-hand rule, I have to twist now the hand so I can align the fingers along the B vector and the hand, the actual wrist, if you want to get the hand, the palm with the A. So B cross A is going to point in the opposite direction of A cross B. A cross B, in other words, I know already is going to be the opposite of B cross A, right? Simply because the thumb will point in the opposite direction if I do the operation in reverse order. So with that, let's stay tuned for the second page. All right, so let's give a formal definition of the cross product. So suppose A is of components A1, A2, A3. I'm not going to repeat the whole system that we did it before for those examples. And let's say B is of coordinates B1, B2, B3. I'm going to give you two definitions, actually. One that makes use of a matrix notation. We'll get to that in a moment. But since in this class, if you take the class with me, I allow the formula sheets, you may prefer actually to write the this first version of the definition. And then I'll show you, in case later on you'll have to memorize it, how you can memorize it faster using matrix notation. So by definition, and let's actually use a different color again, so we emphasize it a little bit, A cross B, right? So notice, by the way, I think I forgot to mention this, the notation for the cross product is the X, right? So that we don't confuse it with a dot product. So A cross B is defined to be the vector of the following components. The first one is A2B3 minus A3B2. The next one is A3B1 minus A1B3, and the third component is A1B2 minus A2B1. Those of you who see this for the first time may be a little bit confused because it seems so random or arbitrary. But again, if you go through the tribulations of doing that system, right, when you try to find a vector perpendicular to A and B, you go through that system and you choose the vector with that orientation I mentioned before and the magnitude that I'm going to talk about in a moment, then you're going to end up with this formula. So keep this in mind. That's the way you compute it. And then immediately let's write underneath the two important pieces of information. The orientation of A cross B is according to right-hand rule A over B, right? You curl your fingers from A over B. Notice I didn't say up or down because it depends on how they are placed in space, right? So orientation of A cross B is according to the right-hand rule. And the magnitude of A cross B, because basically, remember, you can choose any magnitude you want, right? Once you establish the orientation, you can choose any magnitude you want for that orientation perpendicular to A and B. But we choose the magnitude of A and B such that the magnitude of A cross B is equal to magnitude of A times the magnitude of B times sine of theta, where theta is the angle between A and B. Why is magnitude chosen this way? Because it's the most practical one for many applications. Again, as you'll see in a moment when we go over some examples. So that means we have already a couple of extra formulas if you want, right? So let's do a little bit of visualization again. If this is A, if this is B again, A cross B is going to be, A cross B is going to be oriented like this according to the right-hand rule. Let's say this is theta, the angle between the two vectors. And then that means basically sine of theta, let's write it as a sine of theta, because most people will use this magnitude information as an additional formula for the that relates the angle between the vectors with the vectors themselves. So sine of theta basically is going to be the magnitude of A cross B over the magnitude of A times the magnitude of B. So again, the way we chose the magnitude of the cross product allows me to have a formula for the sine of theta. And just as a recollection point, remember dot product was related to the cosine between the dot product is related to the cosine of the angle between these vectors. So there is some sort of similarity between these formulas, so it's better to actually write them down together in some sort of a formula sheet if you prefer. Now make sure you go over carefully with the meaning of these notations, right? So dot product is a real number, cross product is a vector, sine of theta is a real number, but here on the top I have the magnitude of the cross product. So all you see here on the right hand on the sine of theta formula, that's all real numbers, right? Because on the top you have the magnitude of the cross product. Okay, so let's go over the matrix notation. For this cross product. I don't insist on this too much because like I said in class when I teach it, I don't insist too much because I allow people to put formulas on the formula sheet, so you can prefer to just write the definition the way I wrote it here. However, in practice, it's probably better to know the matrix notation because it might be necessary to memorize the way to compute it, especially if you have to do it quickly. So just a quick recollection, remember the determinant of a matrix with 2 rows and 2 columns is given by AD minus BC, right? So I mean, this is like a cross product. Well, I mean, for numbers, cross diagonal if you want. So product over the diagonals, right? A times D minus B times C. So that's the determinant of a matrix with 2 rows and 2 columns. There is also a formula for the determinant of a matrix 3 by 3, which is by expansion of minors on the first row, or any row for that matter. I don't want to detour too much on the way you compute the determinant of 3 rows and 3 columns, but just to give you a quick example, so let's say you have, I mean, usually when I do this in class, I very quickly give an example of how to compute a determinant of a matrix 3 by 3 by hand, because if people didn't study this before, it's too much of a detour, so I don't want to waste too much time away from the calculus 3 part of it. But essentially, there is a way to compute determinants of a higher order, I mean with more than 2 rows and 2 columns, by expanding the determinant as a linear combination of determinants of a lower order. So in this case, a 3 by 3 determinant can be written as a summation of a combination of 2 by 2 determinants. The way you go about it, you can choose any row, by the way, but let's choose the first row because that's going to be related to the way we compute the cross product later. You multiply each element on the first row, so you focus on the first row, and then basically in your mind, but I'm going to do it here so you can see what goes on. Multiply it by the determinant of the matrix obtained by removing the row in the column where that element is located. In this case, row 1, column 1, right? So you're looking at element row 1, column 1. Take out row 1, column 1. What's left is the determinant made by 1, 5, 1, 6. Alternate the signs starting with plus, right? So now with minus. We have 2. Eliminate row 1, column 2. I'm not going to sketch it again because I don't want to make too much of a mess here. So if you eliminate row 1, column 2, you're left with the determinant made of minus 1, 5, and 1, 6. So again, here, eliminate row 1, column 1. Here you eliminate row 1, column 2. Alternate signs again, now it's plus. 3. Oh, I forgot to put 2 here, sorry about that. You take the element on that row and multiply by the remaining determinant. So 1 times 2, and then plus 3 times, now you're going to eliminate row 1, column 3, so you're left with minus 1, 1, 1, 1. And now we can compute these determinants the way we know already for a 2 by 2 matrix, right? So it's going to be 1 times 6 minus 1 times 5 minus 2 times minus 6 minus 5 plus 3 minus 1 times 1 minus 1. 6 minus 5 is 1 times 1 is 1. Here we have minus 2 times minus 11. That makes it plus 22. And then 3 times minus 2, that's minus 6. 22 minus 5, that makes it 17. All right, so that's an example of a 3 by 3 determinant. Finally, what this all has to do with the cross product. Well, we can basically write the cross product using the so-called symbolic determinant. Using also the notation for components in terms of a linear combination of the unit vectors I, j, k. Right? So using that notation, the way to compute the cross product is to set up a determinant, which is not a true determinant. It's basically taken advantage of the determinant way of computing, the way of computing the determinant to basically write the components of the cross product in a much easier way that you can actually memorize. It has also other useful applications. I mean, there are other advantages of this notation that will come up later. But for now, one advantage is if I know how to compute determinants quickly, it's very easy to actually have this notation in mind. That's actually how I memorize myself the cross product, because I will never be able to memorize it the way I wrote it here on the top of the page over here, right? I just have the symbolic determinant in my mind because I can compute it faster this way. So what does that mean? Well, it means that if I actually expand it the way I compute the determinant, then I can quickly recover the components of the cross product that I mentioned before. So first determinant, if I remove row 1, column 1, is going to be A2 B3 minus A3 B2 times I. Alternate the sign, then it's going to be A1 B3 minus A3 B1 J, and then finally A1 B2 minus A2 B1 K. So obviously if I write it in the component form, then I recover, and here I put a minus inside, I prefer to do that, A1 B3, A3 B1 minus A1 B3, and then A1 B2 minus A2 B1. So now I recover basically the definition, I have it on the top. Either way is fine, whichever you prefer. You may see me if you take the class with me live. Sometimes you may see me quickly writing the two vectors side by side, I mean one on top of the other. I mean, I don't even bother to write IJK. I go directly from this to this, right? Because I have the computation of the determinant in mind. All right, so let's finally go over a couple of, well, we're going to write some properties still, or maybe first an example and then some properties and some applications. So let's stay tuned for the next page. All right, so let's take an example. Suppose the vector A is given by 1 minus 1 minus 1, and B, like I said, let's just put them one below the other. And this one, 1 over 2, 1 and 1 over 2. So then A cross B, you should probably pause the video and do it on your own and check with me. Let me write it expanded like that so we can, so pause it, do it on your own and then check with me. So minus 1 times 1/2 minus 1 times negative 1, and then minus 1 times 1/2 minus 1 times 1/2. All right, and then finally 1 minus, because it's 1 times 1, right, minus negative 1/2. Like that. So if we simplify it a little bit, that's minus 1/2 plus 1 gives me 1/2. Middle guy is minus 1, and then the last one simplifies to 3 over 2. All right, so that's the cross product. And here's a couple of questions that I like to ask in class. Very important, simple questions, but very important because they really reinforce the meaning of all of this. It's very important to always remember the meaning or possible meanings, because more often it's not just one of them, of these operations. For now, the geometric meaning of it. So remember, IJK represent the unit vectors that form the standard basis, right, of the three-dimensional coordinate system. Okay, so I'm going to write down a couple of questions, and you should pause the video. I strongly advise you to do that. Think about for a moment, think about the meaning again of our operations of this cross product. Think what you know about the dot product prior, and take some time, 5 minutes or so, and try to answer the questions. You should be able to answer the question directly. There's nothing to compute, just based on the meaning of these these operations. Okay, so let's see. The questions I want to ask are the following. What is I cross J? What is I dot J? What is J cross K? What is J dot K? Here I'm talking about, when I say dot, is the dot product, obviously. What is K dot I cross I? What is K dot I? And let's say we have some arbitrary vectors A and B. What do you think is the answer? What is you think it's A cross B and the answer dot A? What do you think is A cross B and the whole thing dot B? Take 5-7 minutes and see if you can answer this. Maybe in one of these cases you should probably maybe compute if you're not sure. Like for example, let's say one of these I cross J, J cross K, and so on. But for this one, the last ones here, you don't need to compute anything, because I didn't even specify what A and B are anyway, right? So you should be able to answer that quickly. So take a moment and figure it out. And assuming you just did that, let's go over these questions. Now, the middle column here, I hope you remember, we discussed this last time. Whenever two vectors are orthogonal, perpendicular to each other, the dot product between them should be 0. Okay, so the answer is 0 in that case. Now, for the cross product, I mean, it's pretty obvious that according to the right-hand rule, K is in the direction of the cross product of I cross J, right? So I know I cross J is in the direction of K. Now, what about the magnitude of I cross J? Well, remember, the magnitude of I cross J, according to my formula, is the magnitude of I times the magnitude of J times sine of the angle between I and J, which is 90 degrees. Now, I and J are unit vectors. The length is 1, so sine of 90 degrees is also 1. So what is a unit vector in the direction of K? Well, it's exactly K, right? So again, I cross J, I know is in the direction of K because of the right-hand rule. And it's got to be K itself, right? Because as it turns out, the magnitude of I cross J is exactly 1. Now notice that if I change the order of the operation, J cross I obviously is minus K. I don't use this too often in this class, but keep in mind the fact that if you interchange the order of operation, the cross product is not commutative, right? A cross B is the opposite of B cross A. And obviously, the magnitude of A cross B is going to be the same as the magnitude of minus B cross A. Only the orientation is different in that case. By the same token, I hope it's pretty clear that J cross K should be, where is it? J cross K should be I. And then K cross I should be J. I was just making sure that the orientation is correct. All right, so the last two questions here on the right. I hope it's pretty clear that the answer is 0. Why is that? Well, remember, one of the motivations for A cross B is that we wanted a vector perpendicular to both A and B. So obviously A cross B, if you cross it with either A or B, it should be 0 because they are orthogonal. Doesn't matter what A and B are. So with that out of the way, let's emphasize that there are also obvious properties. Again, it's not going to come up that often in my case, but let's say you have the cross product between the summation of vectors, like the distributivity, right? I mean, it still holds like any product, like a regular product, in other words. I mentioned the magnitude So we got that out of the way. Yeah, let's do another application involving the sine of the angle between the two vectors, and then we're gonna actually finally go over some applications to see why we chose the magnitude to be related to the sine of the two. So now let's suppose we have two vectors. Let's say u is given by 1, 0, 1, 1, 0, minus 1, sorry, and then v given by 1, 2, minus 1. And I want theta, the angle between them. And let's actually do it with the two tools we have already at our disposal. So now you could use sine of theta. So in order to use sine of theta, I'm going to need the cross product. So let's do the cross product. Let's do the matrix notation quickly. Oh, sorry. It's gonna be let's see, that's gonna be 2, middle one is -1 minus -1, which is 0. I do it kind of quickly, but always, because I know you guys can pause this. You should always pause and catch up with the computation if you have to go slower in the beginning. So the cross product between u and v is 2, 0, 2. So according to the formula for the sine of the triangle, of the angle between u and v, that's going to be the magnitude of u cross v over the magnitude of u times the magnitude of v. So on the top is going to be square root of 4 plus 0 plus 4 over square root of 1 plus 0 plus 1, magnitude of u, square root of 1 plus 4 plus 1. So I should use a calculator, and this is going to be square root of 8 divided by 4 plus 2, 6 times 2, 12. I can simplify this to square root of 2 over 3. Okay, if you take an inverse sine of this, you should get approximately 55 degrees. Now you may wonder, why do I bother with the cross product? Because I could do the angle by using the cosine angle between them. And that's actually true. I'm saying bother because often people perceive the computation of the cross product to be a little bit more tedious. Not by much, but a little bit maybe. So if you just have to find the angle between them, obviously it doesn't matter which one you pick, sine or cosine. So we should get the same answer. So let's do the same thing with the cosine. Dot product between u and v is 1 times 1 plus 0 minus 1 times -1, that's gonna be plus 1. The magnitude I already computed, root 2, root 6. So theta is gonna be the inverse cosine of 2 over square root of 12, which if you use the calculator should be again approximately equal to 55 degrees. Okay. Let's go over a couple of examples now to actually see why it's actually advantageous to have the cross product related to the sine of the angle between them. So let's stay tuned for the next page. Alright, so this is one of my favorite parts of the class because, I mean, not the only one, obviously there are far more interesting stuff that come up later, but I like that quickly we can actually appreciate how powerful some of these tools are. So let's look at the following example. Let's say we have a parallelogram determined by two vectors. And let's say I want to find its area. So let's say this is u and v. And let's say again, as always, theta is the angle between them. So if I want to find the area of a parallelogram, remember the geometric formula, for it is to multiply the height. Let's say h is the height times the base, right? So area is the height times the base. And let's see how we actually translate this in terms of the vector notation. Well, obviously, and notice, by the way, even if you don't have vectors to start with, nothing stops you, right? So let's say you have a purely geometry problem. You could always come up with vectors aligned with the sides of a figure, right? You can construct a vector to represent one of these sides. So in this case, the height, let's denote it by h, as I said before, and then the base obviously is going to be the magnitude of the vector v. Now, how do I relate the height with the other vector? Well, notice that the height is opposite side in a right triangle. Okay, so that means it's related to the sine of the angle between them. So that means the height is going to be the hypotenuse of that right triangle times sine of theta, right? Theta, the angle between them. But now, remember, we have a formula for the sine of theta in terms of the vectors u and v. So sine of theta is going to be the magnitude of u cross v divided by the magnitude of u times the magnitude of v, and then times the magnitude of v that was there from the beginning. So we can cancel these magnitudes, and as it turns out, the area of the parallelogram is nothing but the magnitude of the cross product of the vectors that form its sides. So here's another direct application, which is very beautiful for us, very concise. I mean, just think about for a moment that if you were to do a problem with classical geometry, you may have to do measurements and some other tools. I'm going to give you an even more drastic example in a moment. But once you have the cross product, it's just computation of the cross product, find the magnitude, that's going to be the area. It's really neat, straightforward, and really, really neat. And my next example, which actually uses both the dot and the cross product, is even more spectacular, although it might not be easy to appreciate it. But it's spectacular because it could be actually a very tedious and complicated problem if you were to do it using classical geometry and not making use of these special operations in vectors. So this next topic is kind of analogous to this one, and it's the goal here is to find the volume of a slanted box. Just to give it an intuitive meaning, the correct name for it is parallelepiped. Piped, I think. I have a problem. So my accent is anyway, that's the spelling. Parallelepiped is kind of like a Romanian accent, because I'm Romanian, but parallelepiped or something. Anyway, we're not going to use this word too often, and because we often want to simplify stuff, I just use slanted box. I mean, this is actually much more suggestive that, you know, the point I want to make, in the sense that this box doesn't have to be straight. That's the point I'm trying to make, because if it's not straight, the volume is not an easy question to answer. Obviously, if it's a straight box, you don't need vectors, right? It'll be just the product of the dimensions, length, width times the height. But that's not the case if the box is slanted. So let's see if we can make a decent picture over here. So just to make it as suggestive as possible. There is a convention to use a dotted line for the stuff that, let's say, it's not visible from your perspective. And as I said, I want this to be slanted like that. And I hope that's slanted enough. anyway, good enough for our purposes. So the most important thing is to imagine that this thing is actually tilted to the right, as if someone stepped on it and ruined the box. It's not straight anymore. So because it's not straight, of course, it's the volume. I mean, the volume is still the height times the area of the base. But the problem is that all faces are not rectangles. They are, in fact, parallelograms. Which means if I sketch the height, let's do it here, it may fall on the outside of the face there. Okay, so let's see how we can do this with vectors. Let's choose 3 vectors originating from one corner of the box. Let's say, and I think maybe we should use again a different color here. Let's say this guy over here is the vector u. This guy over here is v. And this one here in the back, let's call it w. All right, so we have already some powerful tools at our disposal. First of all, so let's write down the volume here. So the volume is going to be the height, h, times the area of the base. Now for the area of the base, because it's a parallelogram, I know already that's going to be the magnitude of v cross w. Notice it doesn't matter the order here, w cross u or v cross w, because the magnitude is the same. It's important to point out here. All right, so furthermore, how do I relate the height with the other vector? Well, let's call theta the angle between the height, I mean the perpendicular to the parallelogram, and the vector u. And notice that it is related to the cosine angle of theta, cosine of theta, because it's the adjacent. If I form here a right triangle, it's going to be the adjacent side of u, which becomes the hypotenuse. So therefore the height, I can write it as, let's start with the cross product, so it's v cross w, and the height, I can write it as the magnitude of u cosine of theta. Okay, now how do I get cosine of theta? That's another problem here, right? Well, cosine of theta, I need to make it, in order to use the vectors, I need to make use of another vector in the direction of the perpendicular. H is just a number, by the way, right? So h is a scalar. But to find a formula for the cosine of theta, I need a vector in the direction of that perpendicular. And to be more precise, in this direction, upward from my perspective. Now pause for a moment and think about how do I come up quickly with a vector perpendicular to the parallelogram upward from my perspective here. Pause for a moment and then realize that it's exactly v cross w, right? Remember the right hand rule, right? So v cross w, it can be any vector, by the way, but it's the default choice if you want to produce a vector perpendicular to v and w. And I need it because I need to, together with u, I need to basically come up with a formula for the cosine of theta. So now I want to use the formula for the cosine of theta. Again, just to make it clear, an angle between u and v cross w. These two vectors form the angle theta. So now I'm going to use the copy the first part, and I'm going to use the cosine formula. What does it say? On the top is the dot product between v cross w and the vector u, and on the bottom is the magnitude of each of these guys multiplied together. Okay, so notice now the magnitudes cancel, and as it turns out, the volume of these slanted backs is going to be V cross W dot U. We still have some remarks to make here, but pause for a moment and realize how neat this is. Okay, I mean, this could be a tedious geometric problem, and we did it very quickly just by essentially applying two vector operations. We're going to show an example in a moment, cross product and the dot product. We still have to make some observation to make the formula a little bit useful. So notice that it could be really tedious. We want to make the formula, by the way, so that we don't have to sketch anything. Notice that if I were to actually label differently, let's say if the parallelogram there on the bottom, let's say I did it W cross V, like that. Then I have to be worried that actually this is going to be minus of the previous answer, right? Because, you know, if I change the order of the cross product, then I'm going to get an extra minus because they are in the opposite direction. Although the volume is going to be the same, but with a negative sign. So that's going to be really annoying, okay, if I have these negative signs popping up if I don't take the order of the operation in the cross product carefully. But in the absolute value, the volume is the same. So that in order to not to worry about it, we're going to have the formula for the volume with the absolute value. And then if that's the case, it won't matter the order of the operation. So the volume will be the absolute value of V cross W dot U. And it doesn't really matter which side you choose as a base. This you could do it like that. You could do U dot V cross W. You could say V dot W cross U, any order you want. Okay, so as long as you choose you put the absolute values on the outside of this operation, the order of the operation doesn't matter. Basically, you do the cross product of two of them and then dot the remaining one in the absolute value, so that you get, of course, a positive quantity, which is the volume. This is also called the triple product in some books. Okay, so with that in mind, let's go over an example on the next page. Okay, so here's an example with the two formulas that we did before. So let's suppose we want to find, let's say, the area of the triangle determined by the points P of coordinates 0, -2, 0, Q of coordinates 4, 1, -2, and then R of coordinates 5, 3, 1. This is actually an application of the area of a parallelogram. The reason is because, and here's the thing, we don't need to sketch anything. I mean, we can sketch a little bit, but not accurately like on the scale. So suppose these are the PQR, these are the points, and this is the triangle, right, that I have to find the area. Notice that if I come up with two vectors starting from the same point, doesn't matter which, right? I chose, for example, PQ and PR. Then I can form a parallelogram, and then the area of the triangle PQR is going to be half of the area of the parallelogram. All right, so I chose this example again to review a little bit of stuff from the previous part, okay? Remember, in all of these tools, we use vectors in the component form, okay? So here I start actually with 3 points. These are not vectors, remember. we have to come up with the vectors ourselves. How do we do that? Well, now if the vectors originate from P, in the component form, that means you have to subtract the coordinates of P to make them in component form from the terminal points. So I look at the terminal point of PQ, which is Q, and subtract the components of P, like that. So PQ in component form should be 4, 3, and minus 2. Same thing, PR subtract 0 minus 2, 0 from R, 5 minus 0, 3 minus negative 2, 1 minus 0, 5, 5, and 1. So then, like I said, the area of the triangle becomes 1/2 the area of the parallelogram, which is the magnitude of PQ cross PR. So all I have to do now is to compute the cross product. They are already one on top of the other. Take a moment and do the cross product yourself. So we're gonna have, let me actually arrange them nicely here, so you can see them in the symbolic form. So it's gonna be 3 minus negative 10, then minus 10 minus 4, and then 20 minus 15. So it's going to be 1/2 the magnitude of this, right, times the magnitude of the vector 13 minus 14, and then 5. Okay, so do this on your own, compute the magnitude. So that's going to be 1/2 square root of 13 squared, 14 squared, 25. You should end up with approximately 1975. Okay, so last example or last application of the let me see a little bit. Well, actually I didn't do, let me see. Yeah, let's do a volume of the box. Let's do a volume of a box. So suppose I want to compute the volume of the box determined by the vectors u given by 1, 1, 1, v given by 2, 0, 1, and then w given by 0, 1, 3. You should do this triple product in 2 ways just to see if you get the same answer. So doesn't matter the order, remember. So let's do, let's say, v dot well, let's do it like that, u dot v cross w. So that's going to be 1, 1, 1 dot, and let's do the cross product now between the other two. 0 times 3 minus 1. A middle guy is minus 6. And then 2. All right, so there's gonna be the absolute value of the dot product of the remaining one, which is minus 1, minus 6 plus 2. That gives me absolute value of minus 8 plus 2, minus 7 plus 2, sorry. Absolute value of minus 7, so that's going to be 5. So the volume of the slanted box is 5. By the way, see, when you do, let's do it in the other way around. Another advantage of the matrix notation. Let's say I want to do it in this order: W dot V cross U. So that means I do the dot product between W, which is 0, 1, 3. And let's arrange here the symbolic determinant for V cross U. V is, so ijk, V is 2, 0, 1, and then U is 1, 1, 1. Now notice that when I expand this symbolic determinant by the ijk, to do the dot product with the remaining one means to multiply each component by 0, 1, 3. So that's essentially, I mean, imagine you have something like this, 0, 1, 3 dot something times I, like in this, well, I mean, the components, right? I plus something times j plus something times k. To do the dot product entails basically replacing I, j, and k with 0, 1, 3 and add them up. So in other words, I can actually come up with a more compact form for the triple product by simply replacing ijk with 0, 1, 3 and expanding the determinant. So if you know basically how to compute a 3 by 3 determinant, that's going to be automatically the triple product. This is just like as a side note, it's no big deal. You could do it the way I did it in the previous step. But I just wanted to point out that the most compact form for the triple product is to basically arrange these three vectors in a determinant of 3 by 3. And now when you expand it, and it doesn't matter the order, right? Again, remember to take the absolute value at the end, right? So when I expand it now, let's do it here. I'm going to have 0 times, let's say 0 minus 1 expanded by the first row. 0 minus 1, it's going to be 0, middle guy, 2 minus 1 with the minus in front of it, and then plus 3, 2 minus 0. So when I simplify this, that's going to be 6 minus 1, which is 5 as expected. So last example is going to be just a quick example or quick application for a cross product, and that's it for today. We're going to talk about the concept of torque. So stay tuned for the last page. All right, so our last application of the cross product is the torque, one physical quantity very well known in mechanics. So let's see how this relates to the cross product. So roughly speaking, the definition of this concept is that, well, I mean, let's actually describe it because that's the most useful way to go about it before we define it mathematically. This is essentially a vector which measures the capacity of a force to exert a rotational force on an object. Intuitively, actually, everybody dealt with the concept of a torque. You essentially, whenever you wanted to screw a bolt or unscrew a bolt, you dealt with the concept of a torque, and intuitively you know how to get a bigger or better, larger torque, basically. So stronger rotational motion given a linear force that you apply on the object. So the model, if you want, with the bolt, suppose for example that over here we have the bolt, and let's say this is a wrench, a rigid, obviously, wrench, and here is the point of force application. So the point where you exert the force to make the rotational motion on the bolt. So let's say, I mean, you obviously intuitively, we'll get back to that in a moment, you'll realize immediately which is the most efficient way to align the force with the wrench. But generally speaking, let's say your force is at an angle with the wrench. So let's denote by F the force applied to the wrench. And to use the notation also in the textbook, let's denote by tau, this is the Greek letter tau, the position vector indicating the wrench. Generally speaking, it's going to be the vector from the bolt to the origin of F, of the force you applied. So intuitively we realize that the longer the wrench, the bigger this rotational force that F will exert on the bolt, right? So the way I drew it here, you're going to expect a rotational like this, right? I mean, from your perspective. So imagine that the bolt is aligned with the page, and then you apply the force indicated given by the arrow there. And then, by the way, the tau, let's actually use some different color here. So tau will be this vector here, the position vector. Okay, so by definition, the torque is defined all right, so let's talk about the torque, one physical quantity which is very useful in mechanics, and that's related to the cross product, as you can see in a minute. The torque basically is a, well, let's actually start with a setup. So let's say you have a bolt. This is like a model because it doesn't have to be a ball. I mean, the concept is more general than that. But let's say you have a bolt and you try to screw it or unscrew it with a wrench. So this is the wrench, by applying a force to that wrench. So let's say the force is applied like that at an angle. Force applied to the wrench. So the goal is to use a force in order to exert a rotational force at a point some distance from the origin of the force, so from the point of application of the force. So intuitively we know already that the longer the wrench is, the bigger this rotational effect and the stronger the force. So basically, if you want to have an easy time unscrewing the bolt, you want a long wrench and or a stronger force. The idea is that, of course, if you have a long wrench, the same force can have a stronger rotational impact on the bolt, therefore a larger torque. So basically the torque measures this rotational force exerted by F. So mathematically, and by the way, let's actually use some notation. So let's denote by R the position vector of F. That means the vector that connects the bolt to the origin of F, right? So I mean, if I let's use a different color here. So suppose this is the this is R, like that. So the torque is defined as, and the notation for the torque is a vector, by the way, just to make it clear. The torque is a vector and is denoted by tau in our textbook at least, and is defined as the cross product between R and F. Sometimes people are confused here because they remember from other classes that the torque is given by some product of some scalars. We'll get to that in a minute. But again, it's important to point out that generally speaking, that is how you define the torque. Okay, it's a cross product between the position vector, which it's the point where the force exerts rotation and the origin of the force, and the force itself. Now, what you want, of course, in practice, you want to maximize or to compute, depending on the case, the magnitude of the torque. That's the one that gives you actually an indication whether you have an easy time or a hard time actually rotating that bolt. But here comes back again the the discussion we had with the conventions in practice, and I hope here that everybody will appreciate the whole idea with the convention with the right hand rule. I'm assuming pretty much everybody who listens listens to this knows that if I want to screw the bolt, I'll have to rotate it clockwise from my perspective. I mean, the way, imagine the bolt is on the plane here, on the whiteboard if you want. So you want to rotate it clockwise for the bolt to go in. But why is that? I mean, why the threads are designed in such a way that whenever you rotate it to the right, it goes in, whenever you rotate it to the left, it goes out. There is no other reasons besides convenience. Obviously, life will be much, much more difficult if the threads will be designed in an arbitrary fashion. I mean, imagine, for example, a car mechanic will have to look at the schematics each time he has to actually unscrew a bolt, and there are hundreds of them probably in a car. Okay, so then the convention is to rotate it to the right. Now, from our perspective, when I say clockwise is when I look at the page and the bolt is on the page, but in fact the convention is right hand rule. Right? Now, going back to the cross product, remember, if R is like that, let's put the forces, because remember, we can move the vectors around however I like, okay? I mean, it doesn't matter where I place them, right? So if R is this way and the force is this way, okay, on the plane, on the whiteboard here, obviously R cross F, according to the right hand rule, makes the torque to be inward to the page, right, from our perspective, because of the right hand rule, as expected. So that's essentially, I suppose, the easiest usefulness of the right hand rule that you can imagine, right? The convention of how the threads are basically designed to correspond to the right hand rule. Now, what about the magnitude of the torque? Well, the magnitude of the torque, which is the one, again, tells you how easy or hard it is to move that bolt, is the magnitude of the cross product, for which we have a formula, remember, that's the magnitude of R times the magnitude of F times sine of theta, where theta is the angle between the position vector and the force itself. And so here comes another very intuitive aspect of the whole problem here. We know intuitively that R and F should be perpendicular to exert the maximum amount of torque, the maximum torque for a given F and R, right? So given a wrench of a certain size, given a force, you want F to be perpendicular, because only the perpendicular component is the one that exerts the rotation, right? If you think about it, the way I sketch here the problem, I mean the force, it's kind of toward the bolt, right? So when I push the wrench in this direction, only the component, the projection, in other words, of the force over the wrench over R is the one that actually exerts some sort of a rotation motion. Now, when is that projection maximized? That's going to be maximized when theta is 90 degrees. Which is to say when sine of theta is actually 1, right? Otherwise, it's less than 1. So the torque will be less than the maximum possible, right? So obviously, intuitively, you know that when you apply force to a wrench, you apply it perpendicular to the wrench. Intuitively, biologically, we feel this in our hands that that's going to be the position that gives me the maximum amount of torque. So let's finish with a quick example. Suppose that the position vector is 1, 1, 1, and the force that is applied to the object is -1, -1, 3. And let's say we want to find the magnitude of the torque. So for this, we're gonna have to find the cross product eventually, right? Because we have to find sine of theta, although you could find theta by other means anyway. So let's do the cross product first. You can find this theta, finding the cosine if you want first. I mean, you have various tools at our disposal now. Cross product 3 minus -1, that's 4. Middle guy is 3 minus -1, which is another 4. And then the last component, let's see, -4 here. So I messed up the sign. 4 minus 4, and the last component -1 minus -1, which is 0. So the magnitude of the torque in this case is going to be square root of 16 plus 16, which is square root of 32. If you are in the metric system, that'll be Newton times meters, right? Because you multiply the units for a force, for the magnitude of a force, which are newtons, for example, with the units for the position vectors, which are meters. What is the angle between them? Let's see actually if it's optimum, right? So I mean, like, if the angle is cosine of theta, let's do the cosine of theta quickly to see the angle between them. So that's going to be dot product between R and F. That's going to be -1 plus 3, square root of 1 plus 1 plus 1, which is square root of 3. 1 plus 1 plus 9, that's square root of 11. So that's going to be 1 over square root of 33. So theta is the inverse cosine of 1 over root 33. And before, let's actually use a calculator to do this. (33) 1 over that, and then the inverse cosine. We're going to get approximately 80 degrees. So obviously it's not maximized. The maximum torque is going to be when theta is equal to 1. If theta is equal to 90 degrees, then the maximum torque possible will be just the magnitude of R, which is square root of 3, times the magnitude of F, which is square root of 11, and that's going to be root 33. But you see, it's not far from it, because 80 degrees is nearly 90 degrees, right? So I mean, you can see they are kind of close to each other, because you're almost close to the best possible position for that force with an angle of 80 degrees. Okay, so I think that's it for today. I'll see you next time.